So now we want to show this. For this case, we want to show that the x is close to this expectation. We already show that this is the expectation of x, and we want to show that the x is very concentrated around its expectation. So as I mentioned before, for that we want to show is that if this expectation is going to infinity as n goes to infinity, then its variance is much smaller than expectation squared. Then we can apply the Chebyshev's inequality. So we consider this claim. So again, we have this x as a summation of this indicator random variable. Is it this way to write the bold one, or anyway? For the indicator random variable, so we know that the x is summation, and then we know how to write the variance of x as a summation of the variance of each one of them, plus the covariance of the pairs of them. And if you have an indicator random variable, what we know is that the variance of y is same as probability of y equal 1 times probability of y equal 0 is smaller than the expectation of y, and covariance of yg is expectation of yg minus expectation of y times expectation of g, which is smaller than the expectation of yg, because this expectation is non-negative. And this is the probability of y and g are both happening, because yg are indicator random variable. So this multiplication is 1 if and only if both event holds, otherwise it's 0. So we have this. So now the main task is that we want to measure this, how this changes over this random variable, the indicator random variable. And so we have this x1 to xb ordered pair, ordered tuple y1 to yb. And if they are completely disjoint, then they are obviously independent. So we don't have to consider its covariance. Covariance is 0. And even if they share one vertex, because the event is about edges, so what happens here and what happens here are independent. So they're independent. But when they share at least two vertices, then the events could be dependent. So if, say, x1 to xp, y1 to yb is the intersection has at most one vertices, then let's say this is x and this is y, then ax and ay are independent, and their covariance is 0. So let's write x is related to this y if this intersection has size at least 2. Then variance of x is same as summation of variance of ix plus summation of covariance of ix iy where x and y are all related. And because of this first inequality, if you just sum up the expectation of the all indicator random variable, then that's same as the expectation of x. And for the latter one, we can actually take x first, and then we take y, which is related to x, and we apply this probability of ax and ay both wholes. Then because this part is same as probability of the first event and probability of the and conditional probability of the second event hold. So you can write this as this way. But note that the events AX are symmetric in the sense that for any x and y, there exists a measure preserving map of the probability space. That permutes the event sending AX to AY. Just meaning that in GNP we have vertices 1, 2, 3, and then this label is not absolutely important. If you map some f from some bijection, if you take a bijection sending this to another, then the probability distributions are identical. So for any ordered set x and y, you can actually find the bijection sending x1 to y1, x2 to y2, and xb to yv. And then rest of them is fixed. For that bijection, if you apply to the binomial random graph, then result has the same distribution. So that means this x and y are not absolutely important. So meaning that on here, for each x you have this term. For another x prime you have another term. But they are same. They must be same. Because you just take a function f sending x to x prime, then all of this probability will be sent to here, and then they must be same. Because they have the GMP has the same distribution after permuting the vertices. So in order to compute this, it suffices to fix x and compute this. So for any fixed x, this must be all same. So we just fix one x and then we just compute this. Then you just put it here, and then this is same for every x, and you can compute it. So now we are focusing on computing this value. So this y can be categorized into several, different things from I equal 2 to say v, where I is the size of intersection. So x has b vertices, y has b vertices. How many vertices does it intersect? We assume that it's at least 2. But between v and 2. So we first consider the case where there are b vertices intersecting. That means the vertices x1 to xb and y1 to yb are identical up to some ordering. As there are at most b factorial over a terms with, say, y's with these, vertices involved are same, and each of them contributes to this, contributes at most 1 to this delta star. So that, counts the, term with the large intersection, which is just constant, and assume the intersection has size I with I being between 2 and b minus 1. Then we have this, say, x, which consists of the vertices inside of x, x1 to xp. And then we have y. And then this part has I vertices. Excuse me. So there are some edges. There could be some edges inside of here. And there could be some edges outside. These edges of H. So in order to get X, so let's put it this way. Let's say H is this graph. And in order to have this AX, you need to have these four edges. X1, X2, X3, X4. And in order to have Y, Y1, Y2, Y3, Y4, where Y1 and X3 are same, Y2 and X4 are same, you need to have these four edges. So there are certain edges which is overlapping here. So, but we have some information about how many edges there are inside here in order to get this Y. As H is balanced, and let's say this S is the intersecting part. S has size I. So this set is S. And most IE over B edges of H corresponding to this AY lies inside S. And the number of remaining edges is at least this of them does not lie in X1 to XP. So why we are saying this? Because we want to measure this. Assume something happened inside of this here. So we have assumed that this is an event which happens inside of here. So we assume this. So we already have assumed what happened inside of this S. And now we want to measure the probability of what happens outside of here. So this is at most P to the E minus IE over V. Because at least this many edges are already outside. So these are independent. These are not yet determined, even if you assume AX happened. So all of them has to be an edge. So it's at most this. But this could be the case that let's say the x1, x2, x3, x4, and for y, we need to have these 4 edges. So in the AX actually does not assume whatever happens here. So in the Y case, we actually have to have this P, this P, this P. And if this happens, then this also has to be here. So this is P to the 4 instead of P to the 3. But this additional one only lowers the probability. So this still holds. So this is the upper bound. So we have this. Then what's this? Probability of A. Now delta star is summation of I is 2 to B minus 1 of big O of N to the B minus I, P to the E minus I over B times some big O of 1. The big O of 1 coming from this. So this is just big O of 1. Because B and A are all fixed. So we fix H, so those are just constant. So what do we have? This is at most, B minus 2 times each of them. Here is N to the V, P to the E times N times P to the E over V times minus I. But what was our assumption? Assumption is that this goes to infinity. So that goes to infinity, meaning that N times P to the E over V is same as N to the V over E, P to the E over V. So this goes to infinity, so this goes to infinity, and you take the negative I, so that goes to 0 as N goes to infinity. So this is this times little of N to the V, P to the E, plus big O of 1 is just little of N to the V, P to the E. So which is little of the expectation of X. So what do we know? Variance of X is at most expectation of X plus summation of all probability of AX times little of expectation of X. And we know that the summation of this probability is expectation of X. So if expectation of X times little of expectation of X is little of expectation of X squared. But what we know is that as we assume this expectation of X goes to infinity, that means this term is also much smaller than expectation of X squared. So this is little of expectation of X squared. So we have this. Now we apply Chebyshev. So this concludes the proof of claim, and now we want to conclude the proof of theorem. Chebyshev inequality. For any epsilon, we have the probability of X deviate from its expectation too much is bounded by the variance of X over X epsilon square times expectation square. And as variance of X is little of expectation of X square, that means that if n is large enough, then this probability can be arbitrarily small. So this proves the theorem. So we have shown this theorem. So in the next video, we will move to another application of the second Moore method.